Namaskar. Hello everyone. This is Pooja and welcome to my YouTube channel. Let me introduce you to various figures and terms that you will be finding quite useful if you want to know the functioning or working of any nuclear radiation detectors. In this video, we'll be talking about the pulse mode in all the detectors where you want to find like energy of the incident radiation. There the pulse mode has to be applied. The pulse height spectra and the total number of pulses N0 represented by the distribution can be obtained by integrating the area under the entire spectrum. The counting curves and plateaus. An experiment can be carried out in which the number of pulses recorded is measured as a function of gain applied, sometimes called the counting curve. Energy resolution, detection efficiency and dead time of radiation detectors. Let us start with the video. Let us now talk about the energy revolution. Revolution. Okay, now let us talk about the energy resolution. So many a times we are more interested to find out the energy distribution of the incident radiation. So these efforts are classified under the general term of radiation spectroscopy. One important property of a radiation detector in radiation spectroscopy can be examined by noting its response to monoenergetic source of that radiation. So figure illustrates the differential pulse height distribution that might be produced by a detector under these conditions. This distribution is called the response function of the detector for the energy used in the determination. So the curve labeled good resolution illustrates one possible distribution around an average pulse height H0. The second curve labeled poor resolution illustrates the response of a detector with inferior performance. So provided the same number of pulses are recorded in both cases, the areas under each peak are equal. Although both distributions are centered at the same average value H0, the width of the distribution in the poor resolution case is much greater. So this width reflects the fact that a large amount of fluctuation was recorded from pulse to pulse even though the same energy was deposited in the detector for each event. So if the amount of these fluctuations is made smaller, the width of the corresponding distribution will also become smaller and the peak will approach a sharp spike or mathematical delta function. The ability of given measurement to resolve fine detail in the incident energy of radiation is obviously improved as the width of the response function, as illustrated, becomes smaller and smaller. A formal definition of detector energy resolution is shown in this figure. The differential pulse height distribution for a hypothetical detector is shown under the same assumption that only radiation of a single energy is being recorded. The full width at half maximum is illustrated in the figure and is defined as the width of the distribution at a level that is just half of the maximum ordinate of the peak. The energy resolution of the detector is the full width at half maximum divided by the location of the peak centroid H0. The energy resolution is thus a dimensionless factor expressed as percentage. So we can say that the smaller the figure for the energy resolution, the better the detector will be able to distinguish between two radiations whose energy lie close to one another. So there can be a number of potential sources of fluctuation in response of a given detector, and all these result in imperfect energy resolution. So these might include any drift of the operating characteristics of the detector during the course of the measurements, the source of random noise within the detector and instrumentation system, the statistical noise arising from the discrete nature of the measured signal itself. And a third source in some sense is the most important because it represents an irreducible minimum amount of fluctuation that will always be present in the detector signal, no matter how perfect the remainder of the system is made. In wide category of detector applications, the statistical noise represents the dominant source of fluctuation in signal and thus sets an important limit on the detector performance. So, the statistical noise arises from the fact that the charge Q generated within the detector by a quantum of radiation is not a continuous variable, but instead represents a discrete number of charge carriers. So, if there are several sources of fluctuation present and each is symmetric and independent, statistical theory predicts that the overall response function will always tend towards a Gaussian shape, even if the individual sources are characterized by distributions of different shape. So, as a result, the Gaussian function given by this equation is widely used to represent the response function of detector systems in which many different factors may contribute to the overall energy resolution. Then the total full width at half maximum will be the quadrature sum of the full width at half maximum values for each individual source of fluctuations. Next, we move on to the detection efficiency. So, all radiation detectors will in principle give rise to an output pulse for each quantum of radiation that interacts within its active volume. For primary charged radiation such as alpha or beta particles, interaction in the form of ionization or excitation will take place immediately upon entry of the particle into the active volume. So, after travelling a small fraction of its range, a typical particle will form enough ion pairs along its path to ensure that the resulting pulse is large enough to be recorded. Thus, it is often easy to arrange a situation in which a detector will see every alpha or beta particle that enters its active volume. So, under these conditions, the detector is said to have a counting efficiency of 100%. On the other hand, uncharged radiation such as gamma rays or neutrons must first undergo a significant interaction in the detector before detection is possible. Because all radiations can travel large distances between interactions, detectors are often less than 100% efficient. It then becomes necessary to have a precise figure for the detector efficiency in order to relate the number of pulses counted to the number of neutrons or photons incident on the detector. So, it is convenient to subdivide counting efficiency into two classes, absolute and intrinsic. Absolute efficiencies are defined as shown, and these are dependent not only on the detector properties but also on the details of the counting geometry, which is primarily the distance from source to the detector. The intrinsic efficiency is defined as this and no longer includes the solid angle subtended by the detector as an implicit factor. The two efficiencies are related by where omega is the solid angle of the detector seen from the actual source position. It is much more convenient to tabulate values of intrinsic rather than absolute efficiencies because the geometric dependence is much milder for the former. The intrinsic efficiency of a detector usually depends primarily on the detector material, the radiation energy, and the physical thickness of the detector in the direction of the incident radiation. So, counting efficiencies are also categorized by the nature of the event recorded. If we accept all pulses from the detector, then it is appropriate to use total efficiencies. In this case, all interactions, no matter how low in energy, are assumed to be counted. In terms of a hypothetical differential pulse height distribution as shown, the entire area under the spectrum is a measure of the number of all pulses that are recorded regardless of amplitude and would be counted in defining the total efficiency. So, in practice, any measurement system always imposes a requirement that pulses be larger than some finite threshold level set to discriminate against very small pulses from electronic noise sources. Thus, one can only approach the theoretical total efficiency by setting this threshold level as low as possible. So, the peak efficiency, however, assumes that only those interactions that deposit the full energy of the incident radiation are counted. In a differential pulse height distribution, these full energy events are normally evidenced by a peak that appears at the highest end of the spectrum. So, events that deposit only part of the incident radiation energy then will appear farther to the left in the spectrum. So the number of full energy events can be obtained by simply integrating the total area under the peak, which is shown as the cross-hatched area in this figure. So the total and peak efficiencies are related by the ratio R, which is defined as this and which is sometimes tabulated separately. So it is often preferable from an experimental standpoint to use only peak efficiencies because the number of full energy events is not sensitive to some perturbing events such as scattering from surrounding objects or spurious noise. Therefore, values for peak efficiency can be compiled and universally applied to a wide variety of laboratory conditions, whereas total efficiency values may be influenced by variable conditions. So to be complete, a detector efficiency should be specified according to both of the above criteria. Dead time. Now let me briefly introduce you to the term dead time of any nuclear radiation detector. So in nearly all detector systems, there will be a minimum amount of time that must separate the two events in order that they be recorded as two separate pulses. In some cases, the limiting time may be set by processes in the detector itself, and in other cases, the limit may arise in the associated electronics. This minimum time separation is usually called the dead time of the counting system. So because of the random nature of radioactive decay, there is always some probability that a true event will be lost because it occurs too quickly following a preceding event. So these dead time losses can become rather severe when high counting rates are encountered, and any accurate counting measurements made under these conditions must include some correction for these losses. So guys, that was all about the general properties of radiation detectors. So these were some of the important graphs and terms that are required to interpret the functioning of any nuclear detector. And I hope the things were simplified. Do keep on watching and do not forget to subscribe to my channel, and please hit the like button, do support us, and do let us know how you feel about the video. Till then, this is Pooja saying goodbye and take really good care of yourselves.